Have you ever just stopped and wondered if the universe has some kind of blueprint, a set of deep, elegant principles that everything else is built from? Well, it turns out it does. And that blueprint is written in the language of symmetry. So let's dive into this beautiful idea and see how it literally composes the very laws of nature.
Okay, so our story really kicks off with this simple, almost poetic thought from the 18th century thinker Pierre-Louis Maupertuis: nature is thrifty. Now, this isn't just some nice-sounding philosophical statement. Nope, it's a fundamental principle of physics. It's this idea that the universe just doesn't waste its efforts. It always finds the most efficient, the most economical way to get things done.
And this slide right here is the perfect illustration of that thriftiness. So if you want to fly from New York to Paris, you'd probably think a straight line on a flat map is the shortest way to go, right? Well, you'd be wrong. The Earth is curved, so the most efficient path is actually this big arcing curve, what's called a geodesic. This is a classic example of what physicists call the principle of least action. It's like nature, whether we're talking about a planet's orbit or a plane's flight path, follows the path that minimizes this thing called action. It's like a built-in GPS for finding the path of least resistance.
And this principle, it's not just for big stuff, it applies to light too. Light is the ultimate efficiency expert. When a beam of light goes from air into something denser like water or glass, it bends. But why? Well, it's because light actually travels slower in water. So the quickest path isn't a straight line anymore. It's the one that minimizes the time spent in that slower stuff. This is known as Fermat's principle, which is just a version of least action that says light always travels the path that takes the least amount of time. So this whole thriftiness idea, it's everywhere, governing everything from planets to photons.
So the principle of least action is awesome for describing how the universe works. But, it doesn't really tell us why. Why is nature so thrifty in the first place? To answer that, we have to go a level deeper. We have to learn the fundamental language of physics, the language of symmetry.
When we talk about symmetry in physics, we mean something really specific. It's not just about, pretty patterns. A physical system has a symmetry if you can do something to it, what we call a transformation, and the laws governing it stay exactly the same. So imagine you're dropping a ball to measure gravity. If you move your experiment across the room, or rotate it, or even just wait and do it tomorrow, guess what? The laws of gravity don't change. The ball's going to fall at the exact same rate. That invariance, that is symmetry.
Now, to handle all these possible transformations in a really rigorous way, physicists use this incredibly powerful tool from math called group theory. A group is basically just a collection of symmetry operations. Think of all the possible ways you can rotate a sphere, for example, that has a consistent mathematical structure. It lets physicists classify and analyze every single conceivable symmetry in the universe. You can think of it as the formal grammar for the language of symmetry.
Okay, so we've got this abstract idea of symmetry, and we're describing it with this abstract math called group theory. But how does any of that connect back to the real world of physics? Well, the answer came from one of the greatest minds of the 20th century, Noether. Her work basically gave us the Rosetta Stone that translates between the world of symmetry and the world of physical reality. And this slide right here, this lays out her core idea, what we now call Noether's theorem, and it is brilliant. She proved that for every continuous symmetry you find in nature, there's a corresponding quantity that is conserved, meaning it never ever changes over time. So take this example. The fact that the laws of physics are the same today as they were yesterday, that's a symmetry in time. Well, that directly, mathematically, implies that energy must be conserved. It's not a coincidence. One doesn't exist without the other. They are literally two sides of the same coin.
And this connection is absolutely fundamental. The fact that the laws of physics are the same everywhere in space, that gives us the conservation of momentum. The fact that they're the same no matter which direction you're facing, that gives us conservation of angular momentum. And there's an even more abstract symmetry called gauge symmetry, which it's a bit much to get into, but it gives us the conservation of electric charge. So the big takeaway here is that the universe's most fundamental laws, like conservation of energy, aren't just some random rules somebody made up. They are a direct consequence of its inherent symmetries.
Now, if you thought symmetry was powerful in our everyday classical world, just wait. It gets even more incredible in the quantum world. When we take this exact same idea and apply it to that strange realm of particles, the fundamental concept is the same, but the consequences, they become so much more profound and, honestly, a lot weirder.
Okay, first, we got to adjust our thinking a little bit. In the quantum world, a particle state isn't a simple position and velocity like a baseball. It's this abstract mathematical object, a vector, that basically encodes all the possible information about that particle, its potential location, its momentum, its spin, everything all at once.
So, a symmetry transformation in the quantum world becomes an operation that rotates this state vector around in its abstract space without changing its fundamental properties, specifically its length, which is related to probability. This is what's known as a unitary representation, and it's how those abstract ideas of group theory plug directly into the mechanics of quantum states.
But, and this is a huge but, here's where things get really wild. Unlike rotating a book, right, where it doesn't matter if you flip it end over end, then spin it, or spin it, then flip it, in quantum mechanics, the order of these symmetry transformations often really matters. Rotating an electron's spin around the x-axis and then the y-axis gives you a totally different result than rotating it around y and then x. We say they don't commute.
And this non-commutative thing, it has real physical consequences. In fact, it's the deep mathematical reason behind the famous Heisenberg uncertainty principle. For an electron spin, the mathematical operators you use to measure spin in the x, y, and z directions simply do not commute with each other. And what that means is, if you know the spin of an electron perfectly in one direction, you are fundamentally forbidden from knowing it in the other two. The very act of being certain about one forces total uncertainty in the others. It's all baked into the symmetry.
So we've seen that symmetry dictates conservation laws, and it even explains quantum uncertainty. But that's not the end of the story. The ultimate revelation is this. It turns out symmetry isn't just a property of the laws of physics. In a very, very real sense, symmetry is the law.
Look at this slide. This is basically the blueprint for almost all of known reality. The standard model of particle physics, our best description of all the fundamental forces in particles, it's built entirely on symmetry. By starting with the simple demand that our universe has to obey three specific abstract mathematical symmetries, and yeah, they have weird names like U1, SU2, and SU3, the fundamental forces of nature just pop out. Electromagnetism, the weak force, the strong force, they aren't arbitrary. They are the necessary, inevitable consequences of these symmetries.
Just let that sink in for a moment. We didn't discover the forces and then find out they had these nice symmetries. It was the other way around. We started with the symmetries and they predicted the forces. The very fabric of reality, the way particles interact, the way atoms hold together, the reason stars shine, all of it is a direct result of a few elegant underlying symmetries. This all brings us to a famous quote from the physicist Eugene Wigner, who just marveled at what he called the unreasonable effectiveness of mathematics. It's kind of this deep mystery, right? Why should our universe be so perfectly, so beautifully described by these abstract mathematical structures like group theory? Why should these elegant patterns, cooked up by mathematicians, be the very ones that compose the symphony of reality? We don't really have the answer, but the connection is absolutely undeniable.
So, from nature's simple thriftiness all the way up to the construction of reality itself, symmetry is the ultimate composer. But this leads us to one final fascinating question. If our entire universe is built on this foundation of perfect, elegant symmetry, what happens when you break it? Well, as it turns out, that's where things get even more interesting. It's a story that leads to the origin of mass itself, but that, my friends, is a story for another explainer.